an online chat room about the lean theorem prover. And there I met these two people, Kevin BUZZARD and Patrick MASSOT, two traditional mathematicians, which means that we usually write pen and paper proofs. All of us are working in some form of geometry. And we sat together and thought, okay, so we ended up here for various reasons, and now we'd like to do something. So we asked some questions. And so our first question was, can we, as a team of 3 traditional mathematicians, actually use a theorem prover and do something non-trivial? The second question was, can these theorem provers, and we were using Lean, a pretty new kid on the block developed by Microsoft Research, and can these theorem provers handle sophisticated maths, whatever that may mean? And the last question was, we'd really like to do something to make other traditional mathematicians sit up straight and say, hey, yeah, sometime we vaguely heard about theorem provers, but apparently you can do math that meets our everyday life in these theorem provers. So, well, we'll have to see. You get to decide. For the second question, it really depends on what sophisticated means. And we had a very simple metric for that back then. It was just if you walk up to a random mathematician and you ask, hey, do you think this subject is sophisticated? And they say yes, then we've done some sophisticated maths. And then how do you make other mathematicians notice? Well, just choose a really fashionable subject. And this was when we were selecting this topic. To be honest, the topic selection was partly already done before I really joined the project, but no lines of code had been written yet. But everyone saw it coming that this guy, Peter Scholze, would be winning a Fields Medal the next year. So he's a German mathematician who has done really brilliant work in arithmetic geometry, and importantly, he introduced the concept of a so-called perfectoid space. And this is a really hot topic, and lots of mathematicians care about this at the moment. So what is a perfectoid space? It's an adic space satisfying certain properties. An adic space is some space that is locally isomorphic to an affinoid adic space. An affinoid adic space is some data attached to a so-called Huber pair satisfying certain properties. A Huber pair is a Huber ring together with a so-called ring of definition satisfying some more properties, etc., 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 etc. And when you explain all of this to Lean, you end up with the following picture. So down here, there's this green star, and that's the node that represents the definition of a perfectoid space. And all these other nodes are in the dependency graph of this one definition. This was a picture that Patrick MASSOT generated at the end of our project. And to be honest, it's not the complete picture, because you can see all these clusters, and one cluster is suspiciously missing, which is basic logic. So we cut away this logic layer from the bottom, because otherwise the graph layout algorithm couldn't make a nice picture of it, because everything is connected to this logic. So which parts of this did we write? Mostly the bottom right here, and all the other stuff was in the existing maths library. Yeah, so we didn't really write much about natural numbers or lists, etc. But and topological spaces were a lot of that was already there. But we did all the stuff on valuation theory, adic spaces. Sheaves were partly copied from another project on schemes, but we needed more advanced sorts of sheaves, so we added those. And then perfectoid spaces. You had these Huber rings appearing in the definition. They're rings So that means there's an algebraic structure, multiplication, addition, but they also come with a topology, and these play nice together. So the addition and the multiplication have to be continuous. So this means you get lots of topological algebra, and then we needed to be able to complete these rings in a very big generality. So that's all kind of stuff that went into this project. So one thing you notice is, well, is this now a sophisticated math that we've done? And we thought this was a really pretty picture. And then Patrick also generated the dependency graph for the definition of the real numbers in Lean. And it turned out to be 25% of the size. So apparently one of the most complex objects that mathematicians care about nowadays is only 4 times as complex as the real numbers. I don't know what this means, but maybe it means that perfectoid spaces can be taught in undergrad classes 3 years from now. No, this came as a big surprise to us. Yeah, so mostly Lean could cope very well with the type of things we were doing. Sometimes we had to really battle the abuse of notation that mathematicians perform all over the place without realizing it. And we wanted to try to replicate this to keep our statements readable. Sometimes we had to sacrifice readability in order to make a statement. Right. So we formalized the definition, and we realized along the way that this is somewhat controversial, maybe. So 2 points must be made. Is this definition actually just a really complicated definition of the empty set? Because somewhere along the way we made a silly mistake, and now can we actually provide an example of a perfectoid space? Well, yes, we can, but it's embarrassingly trivial. The empty space is a perfectoid space, and Lean knows this and agrees. But to build a one-point perfectoid space requires an insane amount of work, and I wouldn't be surprised if it doubles the size of the graph. So we've gone quite a way, and actually lots of components in the existing math library could be reused, but there's still some work to be done. On the other hand, the definition of a perfectoid space in our code is only, say, 20 lines on top of the definition of an adic space. And we do have, in Lean, non-trivial examples of adic spaces. It's just that those 20 lines add some really complicated conditions, and it's very hard to build objects that satisfy those conditions. It just is a lot of work. So we're really confident that our definition of adic space is correct, and then we add 20 lines, and we're really confident that those 20 lines don't contain mistakes. The second point is, to state this definition, we had to prove lots of hard theorems. So, for example, this is a sort of simplified picture of what's going on. I'll take adic spaces instead of perfectoid spaces. So an adic space is a pre-adic space. I just made up that name because these pre-adic spaces don't have a name in mathematics. That satisfies some conditions, namely, for every point in the space, there has to be an open neighborhood around this space such that, okay, this point is inside this open neighborhood, and then there has to exist a Huber pair such that the adic spectrum of the Huber pair is isomorphic to this open neighborhood. Okay, I won't go into what an adic spectrum is, but the fact that you want to state this isomorphism, to make this isomorphism type check, you need to make sure that the adic spectrum is an example of a pre-adic space. And that requires a lot of nasty theorems to prove. So yeah, just if you drill down 3 layers into the definition, you suddenly see lots of theorems appear. Okay, so to get back to our questions, can our team of mathematicians use a theorem prover? I would say yes. but with lots and lots of help from people in the Lean community, and without them, we would certainly not have made it. It was a lot of fun. Can Lean handle sophisticated maths? It depends on what you mean with sophisticated, but if you go to our original definition of sophisticated, then yes, Lean can handle perfectoid spaces and is only mildly impressed, which I think is really cool for the future, because it means we can really do the maths that we care about in our daily lives in such a theorem prover. Of course, there's lots of problems there, but the problem is not that Lean runs out of memory or halts and becomes really slow or something. There are no performance issues. And can we make other mathematicians notice? Yes. We've gotten invitations to speak in colloquia in math departments, to write survey articles for notices of the AMS, American Mathematical Society, also their British and French analogues. And several Fields medalists have noticed and written remarks or made comments. So yeah, certainly people have noticed this and think it's really cool. And we're really grateful for that. So thanks for your attention.
Thanks, Johan. We have plenty of time for questions.
In addition to formalizing the definition of those spaces, did you manage also to prove a new theorem that wasn't known before?
No, not really. I mean, you start with this definition. Okay, maybe we can prove theorems that haven't been written down before, but not theorems that weren't known before. Because like the very first few lemmas that you would prove are so trivial to a mathematician that they wouldn't even care to write them down on paper. But to state the first really interesting theorem would probably require 10 times the amount of work, because there's lots of mathematics that, oh, no, so the statement, not for the statement, sorry. The statement is maybe doable. It would still require a lot of work. But then to prove it that would require a decade at least of work. It's, yeah, that's really blows my mind.
If I may ask a short follow-up.
Oh, sure. We have time to get to everything.
Is this, do you suppose this is mainly because the existing body of knowledge has not been formalized, or is there some intrinsic restriction why handling non-trivial theorems in modern mathematics is so labor intensive in this formalized system?
I think so. We really built a very narrow tower towards this definition, and then if you want to state a theorem that uses a concept just next to this, you need to build up everything that you forgot about when writing this definition. So what we really liked about this experiment is that when we wanted to reuse something that was in the library that for some reason unrelated to this project already existed, we could usually just grab it and put it in and it would work. So that's really encouraging. But of course, there's just lots of stuff that's not in the library yet that we need to do advanced math. So that's the biggest problem, I think. I don't see inherent difficulties.
Why did you choose Lean, and are there other provers that are suitable for mathematicians?
So why I chose Lean, I think it was, I think I stumbled upon some mention that Kevin BUZZARD was formalizing schemes in Lean, and I thought this was really cool, so I just checked it out, and I'm really a novice, and Lean is the only prover that I've used so far. And I would say one of the really big pros in Lean is that the community is so welcoming to people who want to make an effort but don't know anything about programming languages or whatsoever. I mean, we have this chat room. You can ask any silly, stupid question, and you'll have 10 people who answer your question within half an hour or something. It's amazing, and that made this possible. So I would say that as far as I can see, this should perfectly well be possible in something like Coq. And I mean, in theory, all these provers they're sort of equivalent, right? You can embed them into each other. So I don't think there are theoretical problems. Yeah, but Lean works really well for us. I cannot really compare.
What were some technical challenges you faced while
was pretty hard sometimes. And yeah, sometimes we just really didn't know what we were doing and stretching the type class system to the limits. And then if we turned some switches, everything worked smoothly again. So yeah, and like refactoring some part of the code was a completely new experience to us. And you need to make sure that versions of different libraries work together well. But I guess this is all normal for people like you.
So I have a slightly more specific question. So you said that you were using a bunch of concepts from the Lean standard library, I guess a MATLAB or something, and that you're proving.
I would say there was maybe one example. So when it comes to completing these topological rings, there was a version present to complete the rational numbers, to build the real numbers, and build the p-adic numbers. But this was just not general enough. So we really, actually we just needed a new definition that was more general than the previous one. So that's maybe not exactly an example.
Yeah, but it's close.
Otherwise, I would say, yeah, things just fitted together marvelously well.
Okay, maybe we would only notice once you try to prove something about Perfectoid spaces, but who knows?
Who knows?
Thank you.
So there is this belief that set theory is like the ultimate foundations for mathematics. What did you find the most surprising when using, say, type theory? Like, did you feel at home, or did it sound like?
Oh, we certainly felt at home. I think secretly most mathematicians are type theorists. That's not completely true, but when I explain to mathematicians what type theory is about, they feel like it's an extremely natural concept. But when you then explain that, of course, this means that the natural numbers are no longer a subset of the rationals, they think, okay, that's completely stupid. So ideally, you would want to be able to merge the two, right? Yeah, but type theory is very natural to mathematicians. I mean, it's extremely common when you have a talk and someone writes down a statement and there's a variable x and someone will ask, okay, where does x live? This is exactly asking what is the type of x. I mean, the speaker never answers, oh, x is just some set. No, x lives in some bigger space or whatever. Yeah.
So two remarks. So I think this could not have been done in high order logic, because doing abstract algebra and category theory is just hard because you don't have universes. So that's one reason why you would want to use Lean or Coq. I think the other part that we're just starting to understand is the new type class system of Lean, which seems very exciting and seems to solve some of the issues that are there in Coq. Otherwise, I'd like to better understand what's new about this approach that's different from the other big formalizations of mathematics that we've already done in for a long time. So I mean, there might be lessons to be learned, but it would be very nice to bring them out, because formalizations of category theory of big topological algebras. Those have been done. So I think one of the main things to learn about this is the type class system of Lean. That's a very obvious one, but there might be more insights.
Yeah, and I guess that maybe we as authors are maybe not exactly the best people to make these remarks or lessons, because we cannot really compare. We haven't really used the other systems, but this worked remarkably well, I think. I was personally really surprised that when we really started working on this project, because everyone, of course, has 5 other projects he works on, but when we really started to work on this, it was, I think, a matter of half a year, and we got to this really new, brand new, modern definition in mathematics. And I really thought, okay, we'll be working for 4 years on this project. So I always had the idea, okay, to really get to the research level mathematics in theorem provers requires a lot of effort, and we admittedly built a very narrow tower, but we could rise really quickly, I think. So that's what I personally really liked.
So why do you think that would be hard?
Because, well,
there's one metric that says formalizing a carefully written textbook definition. It takes between a day and a week. So if we just take the whole a carefully written textbook of this definition, how many pages is it?
So we used notes by Wethorn, and we didn't even use everything in there. That's 100 pages. But of course, it uses topologie générale from Bourbaki. So you need to do that. So I wouldn't really know if you would really write a blueprint. And then we also built on lots of stuff. So it's hard. But I would say like in 100 pages you would be done. Yeah, and what's nice, these notes by Wethorn were not written with a formalization in mind. Okay, sometimes this also led to issues where we really had to figure out what was going on. Yeah.
Okay. I have a question also about like comparison between set theory and a type theory. But I'm wondering from a mathematician's aspect, do you mainly thinking you are compromising when you use type theory, or you think it's the right thing? Or another way to ask is, if there is a chance to improve the Lean theorem prover or build a new one, what do you want most that Lean does not give you?
So I certainly don't, me personally, I don't feel at all like I'm sacrificing something when using type theory. I don't know the axioms of ZFC. I cannot name them for you. So set theory is something that exists out there, and you can refer to it when someone asks, can you make this precise? But I never use set theory. I just do maths. And what's...
Notations in the language, you say that some notation your mathematicians write them as a very natural thing, but you find that when formalizing that is...
Oh, but you just replace element of symbol by a colon, and the rest works the same. No, really, I felt perfectly at home in type theory, and it doesn't feel as a sacrifice or a compromise to me. No.
Very quick.
Yeah, then what's the difference between set theory and type theory to you, except for the element sign and the colon? What makes a type theory rather than a set theory?
No, yeah, I think when I do mathematics in practice with pen and paper, I use some form of type theory, but very weak, a very weak type theory, I think. But it's not specified, it's not formal or anything. And I think when you do mathematics in practice on a high level, there is no difference between set theory and type theory.
Right, okay, that's what
Yeah.
I think that this is probably a very deep discussion that we should take offline. So let's thank Johan. Also, let's thank Johan for finishing very early, so we had lots of time for questions.